All right, Stefan, you're on.
Okay. Hello, everyone. My name is Steve Neuendorfer. I'm from Xilinx Research Labs. And Fabian has given me a few minutes at the start of his session to give you a little bit of a context about what we think is going to happen with MLIR and hardware design. And I think this will lead in nicely to the talk that Fabian is going to give. So I think everybody has an idea of what software is, and for the most part, this is where most people are putting effort into MLIR today in terms of programming and code generation and things like that. But there's a kind of an equally rich world of hardware design where we're talking about designing accelerators instead of programming them, and things like circuit synthesis and building memory hierarchies and interconnects. And we believe that both of these areas can benefit from having good infrastructure like MLIR that is open source, and it allows us to build good abstractions. Particularly this idea of multiple levels of abstraction is something that is very common in hardware design tools, but there's not a lot of good infrastructure for being able to manipulate those abstractions and today. So we believe that MLIR has a place to fit here for hardware design. And this is particularly important for Xilinx because we build kind of complex accelerator architectures like many other companies. But in particular, we also build devices with programmable logic. And this sort of blurs the line between what is an accelerator that you are programming and what is an accelerator that you're designing or building. To some extent, once we have high-level synthesis, that the programmable logic becomes kind of just another programmable accelerator in our design. At the same time, there's also a kind of a new investment and excitement in open source hardware design tools like Yosis and Verilator, and yet these don't really have a lot of shared infrastructure today. So our hope is that in MLIR we can build some shared infrastructure that will kind of be the LLVM for hardware of the future. So, sort of from a practical perspective, what we see is that there will be a lot of different dialects, and that these dialects are kind of useful in two particular ways from a multi-level abstraction perspective. One is that in order to build a system in the design process, you often need different levels of abstraction. So you might start at a high-level abstraction and eventually lower that down into a lower level of abstraction. But also in a complex system, you also have different abstractions that you might need at different parts in a system. So we might use high-level abstractions at a high level to compose different abstractions that better represent processors or accelerators running in programmable logic. And here I've kind of sketched out a few of the dialects that we think are interesting and some of the connections between them. And our goal is to, this is kind of maybe the first step in that, is to build an MLIR hardware design community that can help work on these dialects and build interesting transformations and tool flows based on them. So at this point, LLHD is not in MLIR yet, but it seems like a good model for starting to build some of these abstractions. So with that, I'll hand it over to Fabian, and he can talk about LLHD.
All right, thanks, Stephen, a lot. Let me actually try.
Before you go on, let me just.
Oh yeah, sorry.
Let me just plus one everything you said. I think there's a huge opportunity here, and there's a lot of, I think the fragmentation that you're pointing out among all the tools, the lack of standard and interoperable IRs for hardware is a big issue. So I think this is great.
Thanks, Chris.
All right, let me quickly share my screen. So I think you should be, yeah, there we go. All right, can you see my screen? All right, perfect. Okay, so, oops. There we go. All right, so thanks, Stephen, for the awesome introduction and lead into LLHD. So my name is Fabian Schueki. I'm a PhD student at the ETH of Zurich. I'm actually a hardware engineer by trade and by education, but I kind of slipped into this IR business here as a kind of side project. So let me give you a quick introduction of what this is about. So basically, LLHD is a hobby side project of mine to come up with kind of a basic low-level IR for hardware design. So actually, if, when I open up my repository, the initial C++ prototypes are 6 years old, so it's been quite some time in the making. The current implementation started roughly 3 years ago after some tinkering. So this all predates like the big MLIR efforts a bit, or at least it wasn't on my radar back then. But I think it can fit into this scheme really well. So in the meantime, the LLHD project has evolved roughly more or less into an IR for hardware design, a simulator that goes along with it, and a compiler which actually translates some of the high-level languages like System Verilog and VHDL into this IR. Then finally, like last fall, 2019, we actually took the time to write this all up as a paper, which now got accepted at PLDI 2020. So there will be a presentation there as well, in case you're interested. And kind of the question for me in regards to MLIR is, can this LLHD, the concept here, can this work as an MLIR dialect? And if yes, can we actually try to make this more of an LVM project? So we have, as Steven said, basically a common ground for building a hardware design community in MLIR. All right, so let's quickly go to the pitch. So in a nutshell, LHD, it's the low-level hardware description. It's an IR for digital circuit descriptions, as an accompanying simulator, accompanying HDL compiler for System Verilog VHDL. It tries to separate the language front ends from the back end in the commercial tools, because these things are really baked into the commercial tools. They disagree, so different tools disagree on various aspects of the languages. Having such a kind of uniform language will make writing these tools much easier, like simulators, synthesizers, place and route, etc. And it will also allow for much more richer and complex HDLs to develop, and also innovation to happen at the language front, which is not really possible at the moment, or only with a lot of hacking and help. So why do we actually need an IR in general? So hardware design is pretty messy. There's a large number of tools that your design flows through. There's simulators, synthesizers, but then you have logical equivalence checkers to verify that things go well, linters, placer routers, etc. Your design has to pass through all of that. Now, the problem with the current existing languages is they're incredibly complex. They're really high level. Some of them are pretty ill-defined. They have corner cases, and it's hard to get a solid, good implementation of these. So System Verilog, for example, is like the main worst offender in this space. Now, on the other hand, there's like a large number of vendors in the tool space, which is by design to a certain degree. However, the problem is that because the standards are really big, there's a selective implementation of the standards, and there's little consensus among the tool vendors how to implement the standards. Now, you might say that there's Verilog, which is kind of the de facto standard for netlists. And I would argue that this is actually not suited as an IR, because there's a lot of implicit operations and implicit casts happening everywhere. There's implicit connections happening, types. The standards are borderline unreadable, and I'm trying to do that with the HDL compiler, but it's really hard to understand the standard and see what all the kinks are of the language. So there's like over 1,000 pages of System Verilog, 600 for VHDL. This is really hard.
And it's not just huge; it's also really bad.
Yeah, it's incredibly bad.
Reading the standard, what it's supposed to do, it's just crazy.
Yeah. So there's like 20 pages describing on how you can make port connections, and there's the wildest stuff in there. It's like no one would ever use that. It's absolutely crazy. So yeah, fully agree. So then, as another problem here for Verilog is it's been merged into System Verilog. So this starts to blur the lines between, okay, what's a netlist and what's like more advanced features like assertions, verification stuff, etc. And there's like no clear interface defined. It's just like 1,200 pages of blah. So this doesn't work as an IR. So how does chip design work today? So basically, as I said, you have tools from different vendors. And this is actually by design to rule out bugs, etc. So what happens is every vendor implements their own subset of the standards. So you have compilers and optimizers in every single tool, which are all coming from different vendors. But the problem is then that the usable subset is actually really small, because if you have like all of System Verilog, you might have like Mentor implementing one subset, Synopsys another, Cadence another, and then what you can actually use is like a really small subset. And there's entire talks at user groups, etc., trying to come up with design guidelines on what parts of the language to use to be at least somewhat reproducible when you move between tools. And this is a huge issue. And last but not least, this really little attack surface, if you will, for novel languages. They're kind of degraded into second-class languages because if you look at the excellent efforts like Chisel coming out of Berkeley or Spinal HDL, and there's a huge host of other languages, they all have to funnel through, for example, System Verilog or VHDL to get access to this whole tool chain. And this is really bad for language innovation, which is really needed in this domain. So how could this work tomorrow? So the LLHD project looks like this. We imagine basically to have one single front end, which is LLHD. You can have a compiler like the Moore compiler, which is the HDL compiler that goes along with LLHD, which tries to get the languages right once, which is a daunting task, but we have to start somewhere, and then maybe this can evolve, etc. So we can implement the languages once. We emit LLHD. Then we can have a uniform way of lowering all these high-level behavioral constructs which are in these languages and lower them to a more structural representation, which is amenable to hardware synthesis and which is easier to understand for the tools. There's simulation also that goes along with that. It allows us to have simpler backend tools because they can just ingest this LLHD language, which is a couple of tens of pages of HTML documentation, and then you're good, and not 1,200 pages of really crazy semantics. And novel languages can target LLHD directly, and as you can see, it's basically every language is a first-class language. It's the LLVM story, so yeah. So as a disclaimer, when I'm going to go through this, the implementation is heavily in flux because it keeps evolving and keeps being adapted to kind of support all the language features that we need in System Verilog. The implementation and the reference manual of the language may be out of sync, and it's sometimes also a bit of a rambling of me as a frustrated hardware designer, having worked with these tools for a long time and dealing with a lot of bugs. All right, so a quick introduction to LLHD and like what makes it different, and also what makes it similar to projects like LLVM. So the basics, in a nutshell, is it's heavily LLVM inspired. MLIR wasn't really back then. So I kind of leaned heavily on how LLVM looked back in the day. It's based on SSA form, has basic blocks, fine nodes. This naming scheme looks similar. Type system is similar, but there's a few different hardware-specific types. Like there's a time type. There's a type for non-power of 2, number of states for FSM. Description. There's a description for 9-valued logic, which is relevant in hardware design when you want to model wires. And there's a pointer analogon, which is a signal which describes how things propagate through time. And we'll discuss this quickly. So at the top, it looks like LLVM. There's modules, which are basically a bunch of top-level description units. It's the root of the design hierarchy, and you can have functions, processes, and entities in there. And these are the 3 main ways how you model hardware in LLHD, and I'll quickly go through what makes them special. So functions are pretty similar to, but it's actually more or less the same as in LLVM. It has many arguments, one return type, and it's kind of like a node for your SSA graph where you can define, have a user-defined mapping from a couple of SSA values to a new value. You can have control flow instructions. They return eventually via return instruction, and you invoke them via call. Now, hardware design is special and differs from software in that if you look at chips, silicon chips, they're inherently time sensitive. So you have signals, they take time to propagate, capacitances have to be charged, etc. And you have digital designs which have a clock, which kind of like stratify the propagation of time and how state progresses. And chips are also inherently concurrent because you have gates sitting next to each other. So there's no like procedure that is being executed. So everything happens in parallel. And this is like one of the key differences to LLVM-IR. It's LLHD models this concurrency and time sensitivity via instructions that allow execution to be suspended. And this suspension can either be time-based, so you wait for a certain amount of time to pass, or it can be event-based. This, together with the following constructs, will make concurrency kind of a first-class citizen in the language. So this is what processes are in LLHD. It's basically a representation of these semantics. So processes are, if you will, a behavioral circuit description. They're similar to functions. It's a collection of basic blocks, control flow, etc. But as a key difference, you operate on time signals in processes. There's a drive instruction which allows you to schedule a value change on a signal in the future. And there's a probe instruction which allows you to sample the current state of a signal at this instant in time. There are two separate instructions, wait and halt, which allow you to suspend execution for a certain amount of time or until an event happens, or suspend execution indefinitely, basically stopping this hardware from operating. And all processes in a design run concurrently, and they can pause as they see fit. Now, in addition to this time sensitivity, there's also a notion of structure and hierarchy. So if you just think about it, placing 10 billion transistors on a die requires heavy reuse, because you're not going to place this by hand or also like in an automated fashion individually. So chips are generally built bottom up. So you have very deep design hierarchies. You have structure reuse by instantiation. So you design an adder, for example, which adds two numbers, and then you replicate that, etc. And this kind of scales through the hierarchy. You have multiple cores per CPU, etc. This translates roughly to copy pasting on the fabrication for the mask. So there's actually a real nice analogy between how the modeling works and how it happens in the real world. Now, these different structures which are copy pasted, they coexist concurrently on the die. So what LHD has to model this is like structural concurrency. So what you do is you can instantiate subcircuits which live next to each other. These subcircuits, they're basically described as a structural data flow. And each instance, each submodule of that circuit executes concurrently. So this makes structure and hierarchy a first-class citizen, which is a requirement to describe hardware. And LHD does this via entities. So entities are basically a structural circuit description. There's just data flow. There's no control flow. You can allocate registers and signals with dedicated reg and sig instructions. You can instantiate subcircuits with the inst instruction. This can be other entities or processes, and everything runs concurrently. And this is basically what is equivalent to the manufacturable hardware is an entity, which is basically a structural description of what happens. So to summarize, the units that you can have in an LHD description are functions, processes, entities. Some of them have control flow, some of them entities that only have data flow. Functions have no real interaction with the physical propagation of time. Processes and entities do that. And basically, these can model very simple snippets of code reuse to behavioral circuits and structural circuits. Now, as I said, only entities are actually manufacturable, and this is why we need additional passes, which I'm going to go into details on how we can basically propagate the design into a format which is more amenable to actually then convert into something manufacturable. So a quick overview of the instruction set. You have your basic data flow instructions. There's constants, literals, bitwise logics. You can have shifts, integer arithmetic, comparisons, value selection. So this is all the basic stuff that you also find in LLVM. And this is easy to share between the two. However, something which is a bit special to hardware is that hardware requires manipulation of individual bits and wires. So there's in compiler IRs, there tends to be a bit of a bias towards bytes and powers of 2 and multiples of 8 alignment of bits. So in LHD, there are instructions to insert and extract ranges or individual parts of an array or ranges of bits on integers, which is a necessity. In addition to the usual compiler IR stuff, you also get control and time flow instructions. The control flow instructions are the same as you would find in LVM. You can have branches, conditional, unconditional. There's calls and returns from functions. You can have phi nodes. And these things only live in functions and processes because these have control flow. Additionally, you can have time control, which can only happen in processes, which are via these wait and halt instructions. Now, the memory model in LHD is very simple. It's basically memory is just a value slot. There's not a lot of pointer arithmetic happening. Basically, you can allocate memory on a virtual stack with the var instruction. You can allocate in free heap memory with alloc and free, and you can load and store values as you're used to. Then to support hierarchy and signal, there's instructions to create signals, connect them, delay them. There's explicit registers, which makes storage in the circuit explicit, which is a big change from the usual HDLs. You can have subcircuit instantiation only in entities, and there's the probe and drive instructions, which can only happen in entities and processes.
Fabian, can I ask you a just kind of
Sure.
framework kind of perspective question here? So I look at it as you have kind of three different things going on. You have the entity and the structural description of the hardware, right? And that's where you have instances, and I think that's pretty well defined within how hardware works. You then have the behavioral side, which I see it as two pieces. One is kind of what I would say like the library of like driving signals and probing things and stuff like that, weighting, like stuff like that. And then you have the wide collection of just general compute instructions like feed nodes and branches and stuff like that. So like if you look at it as those three categories, why did you innovate in the random like branches and stuff like that? Why not just use like Alica and other stuff in LLVM and just kind of just follow LLVM's precedent there? Was that part of your design, or was there a bug to be fixed, or was it just how did you come to that?
It was actually, this was more or less just accidental. So basically, I just threw in a name for allocating something on the stack. And so basically, when I started to work on this, it wasn't really based on. So it wasn't quite clear to me back then how much of the LLVM part you could reuse. So how much of the classic compiler IR translates into hardware. What I did is I kind of started on a clean slate. Now, in retrospect, a lot of these concepts, like the names, nowadays you would just choose the LLVM names or the MLIR equivalents.
Sure, yeah, either way. But I mean, and just to be clear, I don't think that using LLVM IR, the data structure itself, is very helpful here, right? I mean, something like MLIR is better now that it exists, but it's just kind of, it seems like that behavioral side also in Verilog turns into a Turing complete language with all the crazy stuff you could ever imagine in a normal programming language. And so just looking at it as those three layers, I think is helpful, where you have the hardware, you have general behavioral, normal programming languagey things, and then you have kind of this library that's like driving simulation and driving verification tasks specifically.
Yeah, exactly. So basically, what we did also for the paper, and now it's making its way into the code base a bit more, is you can separate these things into roughly like 3 layers. You can have a behavioral layer, which is exactly what you said. It's basically if you have something very LLVM-ish, this kind of caters to pretty much everything that comes out of system Verilog, plus some additional like tweaks. We have a structural part, which is basically a limitation of the behavioral part, which is just what you need to describe hardware. And it gets rid of these like control flow stuff. And there's the netlist part, which kind of like gets rid of all the abstract arithmetic, etc. But I think I have a slide afterwards, if I'm not mistaken, that kind of goes into that. But yeah, you're right. It's like you can have very properly like separated layers on that.
There is another question on the chat. I don't know if you want to take it now in the presentation.
Sure. Let me actually. Apple Keynote is a bit picky on switching out, so let me actually switch over to chat.
It's more for the record. I mean, it's not necessarily the right time to discuss it because you're not done with it. So, as you prefer.
Okay, hold on a second. We're just.
Yeah, we can also read you questions if that's more convenient.
All right. I actually have it on screen, so we'll move to that. Yeah, so that's kind of like, it's really hard to draw a line, and what I found basically is that it's worthwhile to kind of capture the existing IR like HDLs in a language which is like distills what is currently being done in hardware design to the kind of least amount of surface area, and then a lot of other like higher level concepts on how you map things to processes or functions, etc. You would have as a kind of, as Stephen also suggests, as a kind of other dialects which go into the mix, and you would lower from those into kind of LHD as the basically last line of before you move into more of the hardware design realm.
Okay. Yeah, if it's a pretty low-level abstraction, then the latency and sensitive aspect is probably less critical. I mean, I'm not an expert. I can imagine there are some technological nodes that make it important again, but
yeah, it's so
the
problem is you need a lot of the stuff that is currently in LHD is it's pretty much inspired from what we've been doing in hardware design for the past 20 years, and there's a lot of it's a really messy business, and you need some notion of time for the simulation part and to cover the real dirty back end of hardware design, and to kind of move into this flow. That's probably also why it's worthwhile to kind of have a good separation between what is really close to hardware and represents more of in a structural way what is going to be on an FPGA or a chip from a more high level description. So
agree. It's hard to for sure.
Yeah. All right, thanks. So basically, this actually is a good lead over into how we actually map current HDLs to LHD.
I'm sorry, I have a small question. Sorry.
Sure.
Are you modeling synchronous hardware or more general stuff?
It's more general, actually. So what you can do is you can model synchronous hardware, and there's the register instruction, which basically allows you to specify triggers on when state changes, and this directly models a flip-flop or a latch or different combinations thereof. There's a lowering pipeline, which I'm going to introduce in just a few seconds, which actually can take your behavioral code that's coming out of System Verilog, the high-level way how we describe this at the moment, and map this into a more explicit form. But it's not limited to synchronous hardware in that sense. So basically, whatever you can describe in System Verilog, for example, or in VHDL, you can also describe in LHD. And this was one of the design goals, because when I started working on LHD, Chisel was just being a thing that's coming out of Berkeley, and they have an IR right now, which is called Fertile, which is very much tuned towards synchronous design. Might actually have been relaxed a bit in the meantime, but back in the day when I looked at this, it was very much just a description of synchronous hardware. So one of the design goals, and I talked to the guys back then, and basically that was their design goal, to have this kind of fertile backend. So one of the design goals of LHD actually was to kind of retain this generality which we have in current HDLs, which is a necessity if you want to kind of have the hardware design business actually step into this and then kind of get involved.
Okay, so you want to keep, like in MLIR, a sort of partial specification of the semantics, not full specification.
So it depends on what you mean by partial specification of the semantics.
Well, it seemed to me that in MLIR, semantics is defined by lowering. You don't have an operational semantics. If you introduce an operator, you can define its semantics by translating it downwards, and then it's whatever you produce.
Yeah, that's true. So at this level of abstraction for hardware, what you usually do is you have your building blocks for hardware is your standard cells in case of an ASIC, etc. So basically, you would lower to this level of abstraction, and then LHD has representations for high-level arithmetic, which is usually what hardware synthesizers capitalize on to drive a lot of their optimization. So this part is really geared towards the hardware design space. Yeah.
So what I'm thinking is things like that I saw when I was young, which is people trying to make sure that their simulator is doing the same thing as their hardware. And there was a notion of high-level semantics of the specification, and then you made sure that it goes down well into the software that simulates and into the hardware that implements. Here since you only have a semantics by lowering, then it's more difficult to do that.
Yeah, the unfortunate story in hardware design at the moment is that this is more or less the current, like the way it's done. So usually you have in your whole hardware design pipeline, you have your simulators which simulate everything, etc., and you have your logical equivalence checkers which will actually compare your hardware as it moves through this pipeline of being lowered, if you will, by synthesizers into netlists, etc. But the problem there is that the thing you're always verifying against is system verilog with a very high level, very ill-specified set of operations, etc. And LHD in that sense is more or less a proposition of coming up with a simpler, distilled down version of whatever you can describe in system verilog and VHDL, and mapping those to this abstraction. And then what now happens is, to verify everything, you take your system verilog or VHDL and then you move it through these different tools, and you hope, and it's really hoping, that the tools kind of agree. And if your logic equivalence checker says, okay, things are equivalent, you hope that it understood your RTL the same way as your simulator did. So what LLHD proposes is that rather than doing this crazy operation on system verilog, let's actually have an intermediate node which makes it much easier to compare things. And since verification happens against this RTL level anyway, at least when it comes to hardware manufacturing, it's much easier to map everything into this lower level representation, which has very clearly defined semantics and it's very simple to understand, and then use your simulator to simulate it, your logical equivalence checker to check it for the hardware that you actually produce. And then at least you're sure that whatever you've been simulating is now also what you've been given in hardware. And then the mapping from system verilog to LHD is kind of like left as a separate problem, but it makes the verification process much easier.
I think there's another huge benefit as well, which is standardizing some of that IR infrastructure, because there's so many tools and they're all weird in different ways. And I think there's two sides of it. One is that the tools don't agree because they implement different parts of the standard in different ways, but also that they have bugs. Right. And so the way, I mean, bugs are inevitable, but the way you reduce the amount of bugs is by reducing the amount of code. The way you reduce the amount of code is to get people to use more shared infrastructure.
Yeah, we could even have like a bug point for, like, if the two simulators disagree, figure out, which part of the code is producing the disagreement.
Yeah, doing that with Verilog today as a text form would be insane.
Yeah, that's borderline insane and possible. So that's absolutely crazy. That's also why I think LHD is interesting also in the verification front, because now we do this crazy thing of verifying the very high level language, and you have to trust that the lowering that the logical equivalence checker of your crazy behavioral description to like some SAT solver, like some verification formal problem, that it gets this right. And the next tool gets it right as well, is much more crazy proposition than saying, okay, let's map everything to a lower level, then we verify that level, and then we check against that level, and then at least we know that, yeah, stuff works there. All right. Cool, awesome questions. So thanks a lot. Keep asking. So let me quickly step you through how you would map an HDL to LLHD. So a lot of the examples, they're also in the paper, which I've linked, etc., in case you guys are interested. So actually, this kind of is it's a good lead-in from the discussion before. So the state of hardware design at the moment is basically hardware and test cases are written in system verilog and VHDL. And the key part here is that test cases are also written in system verilog and VHDL. Unless you're like doing some crazy low-level stuff like hand drawing transistors and verifying stuff at the electrical level, but that's like out of scope. I'm also currently ignoring a bit the excellent efforts that are coming out of Berkeley with Chisel, etc., which kind of ties in nicely with LHD actually. So the hardware world is really slow and conservative. Everything is built around this first time right principle because silicon is expensive. You can't do respins. You can't do like prototypes really well, etc. So the whole system verilog VHDL legacy must be part of the story we have to kind of like abstract this and build like a uniform infrastructure. So let's look at like as a running example, a very similar simple accumulator in System Verilog. So that's basically a piece of hardware which has a clock input, it has an X input and an enable input, and then whenever the clock ticks and the enable input is high, it will add up whatever the input X is. So it's basically an adder circuit. And this is like a very simple piece of synthesizable code that you would get in System Verilog. And this is what you would put into a synthesizer, generate hardware, etc. But on the other hand, you also have test bench code. So basically, you have a test bench for this accumulator, which instantiates the accumulator, generates some inputs, checks if the outputs are okay. There's some like functions being called, etc., to do the checking. There's assertions which will break or fail during assertion, during simulation, etc. So a lot of the code is in System Verilog is test benches, etc. So this is a significant part, and we must be able to kind of keep this in the IR as well. So how do we map the synthesizable code? So this is basically what other IRs in the hardware space are focusing on a lot. So like Fertile is very much focused on synthesizable code, or it was back in the day. And like all the IRs that come out of, for example, Yosis, they tend to focus on synthesis, which is clearly what the tools are built for. So in this case, the outer module, this we would map to an entity in LLHD with the same inputs, the same outputs. The signals, the local ones, D and Q, they would get explicit signals. The always FF process, which is a process in System Verilog, which is intended to describe a flip-flop. This we map into an LLHD process. There's an at operator which allows you to wait for an event to happen in System Verilog. This translates into a wait instruction. There's a PosEdge qualifier which checks for a positive, like a rising edge on the clock. This you can translate into LLHD as a basically sequence of arithmetic and logic instructions. You can have drives which actually schedule that the signal Q should change to the value D in 1 nanosecond. This you need to retain. Then always comp, this is also a process in System Verilog, but it's intended to describe a combinational logic. So this has no state. This is basically a mapping from inputs to outputs. This maps to a process as well in LLHD. You can have your control flow, etc. here. You have your drive instructions. Your ifs become conditional branches, and your drives become state drives, basically. The mapping test bench codes looks a bit different. Roughly, the module gets mapped to an entity again. You have your local signals. Your instantiation of the accumulator to check becomes an instantiation in LLHD. The initial, which is again a process in System Verilog, gets translated to a process. You have your local variables become your stack variables. You can have your drives, etc. Explicit waits in System Verilog, which suspend execution in this process. They become a wait in LLHD. You can have your function calls. Functions remain functions when lowering, and you can have built-in assertions, for example, which break during abort simulation if they fail. These we currently model as intrinsics. So this is all a lot of code, and it's really high level. It has a lot of control flow, etc. So this doesn't really translate into hardware directly. So LLHD comes with an optimization framework. It's basically the optimization concept is similar as LLVM. You have a few well-known passes. If you start from behavioral LLHD, you have your constant folding, decode elimination, common sub-expression elimination, the usual business. There's a few hardware-specific ones like total function inlining, desequentialization, etc. I'm going to show you what these do in a bit. So the key goal here is to take the behavioral code that HDLs emit and map it into structural code, which is manufacturable. So this is actually, this whole process of optimization is much more important in hardware than in software, because essentially your compiler runtime budget is huge compared to software, and having a good optimization result is kind of key. So this is why you can actually put a lot of effort into optimizations and trade a lot of runtime for that. But that's not really the case at the moment.
How well does mapping behavioral to structural representations work? I assume you can't map all inputs.
Yeah, that's true. So there's at the moment there's transformation passes in LLHD which do this mapping, and I'm going to show them to you in just a bit. Actually, there's constructs and ways of describing behavioral code, like the test bench code, which never translates into structural code.
Right.
And the way this is handled at the moment is you have your transformation passes, and they will do a best effort without blowing up the code crazily to lower things into structural code. And then that's basically your optimized LLHD. Then if you want a synthesizer, for example, you have a separate pass which kind of adds additional transformations like complete and total loop unrolling, total function inlining where it's applicable, etc., and stripping out a lot of like these assertions, for example, verification constructs. And then this transformation at the end, you would do a verification step and check if you only have entities left in the design, which is basically the sign that it's now structural code.
So why is that useful? I mean, what you just described is, so let me restate what I'm hearing through this is you have a process which sometimes works and sometimes through heroic techniques that are very difficult for a programmer to predict, that then can give you a syntactic sugar that is not very tasty. You know, basically. I mean, is that a fair characterization, or do you think that's not fair?
It's a fair characterization, not only of LHD, but of the hardware design space in general, actually, at the moment.
Yeah, I mean, it's like it's treading into HLS territory, but not really going there, and you know, it's just kind of an interesting.
Yeah, the problem is that this is actually how it works at the moment. So the way, like, if you look at VHDL roughly predates digital hardware design, more or less, right? And then being able to describe hardware was kind of slapped onto VHDL, and then at some point, like Verilog came along as a kind of extension or replacement to that, etc. And a lot of the stuff which is actually really essential and key in hardware, like state, flip-flops, etc. In HDLs, this is like implicit behavior that your synthesizer has to infer from how your like flip-flops are described, etc. So this is why this stuff is really messy, and a lot of things which you would say, okay, that's crazy because in hardware this is essential, so there must be a very clear mapping from one to the other.
Yeah.
The problem at the moment is that the hardware languages that we have, they don't provide that.
Yeah, they're just not good, basically, right? I mean, they're not good in any objective metric I've seen, but
I completely
yeah. Well, I mean, I think it's true. Right? There's a huge amount of there's a huge amount of legacy in these HDLs, and most people agree that they're not actually a good way of actually just designing hardware. But they happen to be what are widely used in the industry, right? So they're on the language design level. I think there's still a huge opportunity to do something better, which maybe is a separable question from what Fabian is trying to talk about in terms of hardware.
Yeah, when I was on a hardware team, I was told by one of the hardware folks that apparently every hardware group has their own sort of macro language or some sort of solution to like wrap embedded Perl snippets into their Verilog or something like that to make it work. So I think you're right, Chris.
I just wanted to do a time check, Fabian. We have roughly 10 minutes left.
All right. I'll stop bugging you.
Yeah, and there was one question online on the chat, so I'm just going to read it for you, which was,
sure. Please do.
How about hardware-specific optimizations such as retiming? Where do they happen?
So they don't happen in LHD at the moment. They can happen on the structural part of LHD. But actually, I had a discussion with Steven recently on that. And the problem with retiming is that you need a lot of like side channel information, and it's really hard to retime in general. So for example, a lot of synthesizers, when they do retiming, they would consider like the actual gate delays to balance out delays. And then the question is, how do you implement an adder or a multiplier, etc. So there's like a lot of stuff going on. And the way you can do retiming is you can do it on something like LLHD. But to me, it's not clear yet how exactly that would happen and how you transport the additional information, like this technology specific information on, okay, how long does an AND gate take or an adder, etc. So these transformations are really opinionated, and to me it's not yet clear how they fit, where they exactly fit into the model. So you can do it with LLHD, and you have all the, basically, if you take structural LLHD, which is basically, as Chris says, like structural LLHD is basically the essential hardware angles without all the crazy mess that current HDLs do. So the behavioral LLHD, which is actually just like 4 or 5 additional instructions, is to cater to the high-level HDLs. And then structural LLHD, which is just a few instructions less, is basically a more sane representation of hardware with registers, etc., explicitly. But stuff like retiming goes in there, but it's, to me, it's not clear if that should stay in a synthesizer because it's really far down in the synthesis pipeline, or if there's like a general implementation of that which can be done on like a high level. Probably more on the FPGA side, which has a bit more like it's easier to predict, I would assume. But yeah. All right, let me quickly step you through a few of these steps and how this fits into MLIR. So basically, kind of to answer also Chris' question, like how we go from this crazy mess into something which is more usable in hardware, is you do the usual transformations, etc. Then as a first hardware-specific pass, LLHD has early code motion, which is similar to loop invariant code motion, but it's more eager and designed to hoist instructions into predecessor blocks as far as possible. So we can do that. This moves instructions up. As a second step, there's temporal code motion, which tries to make the drive instructions conditional and push them out of branches so that they are always executed and not only under certain conditions. And then you have total control flow elimination, which is usually just that code elimination. And as soon as you have a process in this very simplified form, you can actually apply process lowering, which converts it to an entity. And now this is like a more sane representation of what you would want to have when you work with hardware. This is also what you would emit if you design Chisel or a new language, for example, a new HDL. You would probably target structural LLHD. Sequential processes are a bit more tricky. You also apply this early code motion, which basically tries to move things up as far as possible. You can have temporal code motion, which tries to push drives down, introduces auxiliary blocks where needed. Then desequentialization detects this implicit flip-flop or latching behavior, which is this crazy property of HDLs, and turns everything into an entity with explicit registers, which is what you want to have in a hardware description. So how do you play with others? LLHD actually is you can use to feed into EDA tools. A lot of that stuff is still under development, but a lot of the EDA tools have their own IR. Most of them are accessible to the user via some way. So the way you can interface with them is as soon as you have structural IR, LLHD, you can actually, there's a more or less direct mapping from structural LLHD to a lot of these IRs, which you can then feed into the tools. There's more, which is the HL compiler that I've been writing. It's basically inspired by the Rust compiler, but it's just like a side note. So basically, when you provide it with some system Verilog and some limited VHDL, it can produce LLHD for you. The LLHD project itself comes with a set of CLI tools. So there's like a checker that checks for well-formedness. There's an optimization runner. There's a conversion tool, which is working towards supporting all of these languages that you see on screen to convert between those formats via LLHD as a kind of intermediate representation. This is heavy work in progress, so not all of that is implemented as we speak. And there's LLHD, which is like a reference interpreter and simulator to actually execute your LLHD and produce a VCD trace of it. And now kind of like the interesting question to me is, how can this fit into MLIR, and how can this fit into MLIR? The way I see it, also like Chris's comment, is kind of like also going into that direction. The behavioral part of LLHD, which is kind of like the full instruction set, what LLHD offers, that's probably too specific to system Verilog and VHDL, and there's little benefit of that in MLIR, or there's not a lot you can leverage. However, I will argue that the structural part of LLHD, which is more or less behavioral minus 2 or 3 instructions, is a good candidate for a general purpose IR for RTL. because it has explicit registers with different semantics, latches, regular registers, dual latch triggered registers, etc. So this could be an RTL dialect, if you will. And the netlist LLHD dialect, which is a very restrictive set of LLHD, could be basically the netlist dialect for MLIR. There's been a recent discussion on the SSA dominance condition, if that can be relaxed. So there was a discussion on Discourse on that. So like in a nutshell, if you have FSMs in your hardware, they basically necessitate loops, or they build loops in your data flow graph. LHD itself gets around this by having the probe and drive instructions. So this breaks loops at signals and registers. So this kind of gets around this. However, if we relax the SSA dominance condition a bit, you could actually have loops in your graph and describe hardware more concisely. And this could be an attractive change on how you could describe a netlist or a structural LHD netlist in an IR. It's probably not as general, so I don't think these are entirely equivalent, because there's a few crazy hardware design things that you probably can't describe, like tri-states, buffers, etc., like wired ANDs, wired ORs, but that's not really relevant. But it makes the single driver principle explicit, which is basically predominant in all of digital design, and this tri-state stuff is only corner case. So it could actually be good choice to have something like this in the IR, which actually enforces a certain sanity in the hardware, and it's easier to optimize. So you can try this for yourself. There's a website, has a playground, language reference manual is there. You can type in some system Verilogs. It will spit out some LLHD. You can toy around with that. It's completely unoptimized LLHD, so you see all the gory details. You can take a plunge with more if you want. You can just clone it, build it, and have fun with it. And yeah, thanks a lot for your time. And thanks a lot for your questions. And please shoot if you have any additional questions.
Comment online is super impressive pet project. That's in between quotes, because it's very impressive indeed. Thank you. Thanks a lot for this. I found it very fascinating to see this, and it seems like there's a lot of opportunities for MLIR there. We only have 3 minutes for questions, but
can we have the slides?
Yeah, absolutely.
So as usual, the slides on the recording will be online. They will be posted on the mlir.rvm.org in the next 2 days, and they will be found in the agenda for the presentation as well.
And maybe those of Stephen also.
Sorry?
Maybe those of Stephen also in the beginning.
Yes, Stephen, if you can send them to Pankaj as well.
Yeah.
What is the current state of the More front end? How complete is it?
So I'm from Luca Benini's group at ETH, so I'm trying to get it to ingest most of what we do. It's currently a bit biased towards System Verilog, but it's as we described in the paper, we have this very simple but efficient RISC-V core, and it can completely describe this RISC-V core, and it can completely map the Verilog of that RISC-V core to LLHD, which then simulates in the simulator. It's constantly evolving. It's crazy to implement System Verilogs. Yeah, surefire way to ruin your holidays, but it's evolving.
You mentioned at some point that state encoding is something that is left to the HDL tools in the backend, right?
Yes.
So how would you lower information from the behavioral level to guide your state encoding afterwards?
So the way this is done in HDLs at the moment is usually you have attributes that you can annotate in the HDL. So there's no way in HDLs how you can, in a standard way, annotate this lowering information, but there's a general purpose mechanism to have attributes assigned to certain parts of your HDL. And at the moment, there's tool-specific annotations for what you describe, how to map states, etc. However, this you could come up with, for example, a standard metadata annotation on your LLHD which conveys this information further down the pipeline.
Okay. Just another question, since how about unstructured optimizations, netlist like optimizations? Would you also guide them using? So are they also completely outside LLHD?
At the moment, yes, because netlists are a bit weird because they're kind of like your JSON of hardware, because really there's no semantics and you don't have any you don't have any arithmetic, any logic operations, etc. So all the information you need is coming from the outside, and as in the form of like library files which describe what the individual instantiated gates do, etc. There might be an opportunity to fuse this into LLHD, but it's a good question, actually.
When you're doing things like state machines or arbiters or arbitration rings or something like that, you would want to optimize the whole object, right?
Yeah, that is true. And you could still do that. And it depends on what level you want to do that. Probably not on the netlist level, because so at the moment LLHD doesn't really try to replace the synthesizer, because it's a huge task and it's very difficult, and the whole mapping from the structural kind of description with arithmetic inside, etc., to a netlist of actual instantiated gates in your ASIC or FPGA technologies is really difficult. And there's been like 20 years of multi-billion-dollar like research commercially into that, and a lot of these optimizations that you described, they would fall into the domain of such a tool.
Okay.
It's hard to kind of pull this out of those tools, but I'm not saying that we can't have kind of like a more generalized framework where some of those optimizations which are common can actually bubble out into a more like general purpose open design framework. And I'm actually hoping that this will happen.
Thanks.
All right, we're out of time. And I think we had time for a lot of discussion and question along the talk. So thank you again, Fabian, and thanks everyone.
Thank you for having me.
We're going to try to get this online as soon as possible. Bye, everyone. See you next week for another.
Bye. Thank you.
Nice evening.
You too.